So this week we're going to talk about thunderstorms. Well, if you're going to talk about thunderstorms, you might as well look at what's going on with thunderstorms right now. There is not a lot. There is some down in southern parts of the U.S. right here, across Alabama, Mississippi area, and there actually is a tornado watch right down on the border here of Alabama and Mississippi and the Gulf of Mexico. So something a little bit going on down there, we could say. So what is going on? What causes thunderstorms like that? We can see it in the radar here. You can see these line of thunderstorms in that area. So if you were to look at what's going on right now, well, I thought I'd look just at moisture convergence. We've talked about convergence being uplifting of the air. Well, say I bring uplift to the air, but I also bring in moisture at the same time. By bringing in the moisture at the same time, what I am doing is enabling more instability to that air. I'm forcing it to go up, and I'm increasing the instability at the same time. So one of the things meteorologists look for is moisture convergence. And we see that basically right down in that little area right in here. A little bit better off the Gulf Coast, but not a lot. And that's an area we would expect thunderstorms to actually pop up and develop with time. There's some off the east coast of the United States here where the Gulf Stream is. Not a bad place for it. So another part of looking at this is going to be wind shear. The more wind shear, and all eventually. Right now we'll look at instability. So this instability right here is around 3,000 joules. Very unstable air off the Gulf of Mexico. Coming in. You notice the winds are out of that direction, advecting in there. And you can see this fine line of showers and thunderstorms developing in that area. So you bring in a little bit of instability. We have moisture convergence there, so we have air lifting that area. And finally, we wanted to see if there's any wind shear in that area. And yeah, there is some wind shear. Not great. About 40 knots. We want usually closer to 50 or 60 knots of wind shear. And yeah, we need all the other parameters to go along with that to have a good chance at severe weather. But 40 is borderline. So where we're seeing this fine line developing here is where we're expecting. Oh yeah, there's also, if you were to look at the surface map right now, there's a weak low right there with a cold front coming down this way. Here's another one of these extratropical lows, as we talked about this past week. So let's move on now to the slideshow itself here. So what conditions in the atmosphere actually cause the development of these severe weather? Well, we just looked at some. But let's really begin to look at just what a thunderstorm is. Thunderstorms actually don't last that long. If you think about the development of an individual thunderstorm, you're really talking less than an hour's time that thunderstorm probably began, reached its full strength, and was dissipating. That's not real long. Notice here the first part of it, towering cumulus, the thunderstorm's going up. Really may not even be raining at this point in time. Here it's reached its fullest stage. Oh yeah, part of the winds are now coming down. This would be the front. If you were looking at it coming towards you, this would be the area you'd be seeing. And this would be behind it where the rain is coming down. And eventually all you have is wind coming down out of what's left. So if you were to take that as a timing, you're probably looking at 10 minutes, 15 minutes to have this happen, another 15, 20 in the mature stage, and another 10 or 15 in this stage. The whole thing under an hour. So there are different classifications for thunderstorms. We talk about single cell, which is what we just showed you. Then there's multi-cell clusters. All right. They work together, literally in combination, to keep a series of thunderstorms going. That I showed you down in the Gulf of Mexico and along the coast with Alabama and Mississippi. That's like a multi-cell line, very similar to multi-cell cluster. Each one of those thunderstorms helps to keep the other ones going. That's why one individual thunderstorm along that line may continue to last for hours, whereas one individual thunderstorm out in the middle of summer may only last less than an hour. And supercells are the most intense. They are where your tornadoes threat occurs, your risk of hail increases. These can make probably 3,000, 4,000 cape and wind shear of 50 to 70 knots. All of that coming together with some strong lift to produce these. And they tend to form out ahead of a line or out ahead of a group of thunderstorms. They're by themselves. So when we're looking at a radar, you want to look for supercells. You look for individual cells that are out ahead of where the main area thunderstorms are. These cells tend to be rotating, and they're going to have very, very strong updrafts. Here you can see the multi-cell tendency. Cells always will tend to form closest to the moisture. Moisture around here is typically in the southern part. So multi-cells will tend to form in the southern part, reach their maturity further up along the line, and dissipate on the northern end. And here we talked about again, you need some good sources of lift, instability. Solar heating definitely drives this. The hotter the day, the better chance there are severe weather, especially if you have moisture. And here you can see where they typically occur. Everywhere in the United States gets them. Even all the way up into Alaska will get a few thunderstorms each year. And you can see they're less along the California coast, much more down in Florida. So why does Florida have them? Well, Florida starts off, it has a warm body of water in the Gulf of Mexico, has a Gulf Stream right on the east side of it, both warm. And they get a lot of sea breezes, both from the Gulf and from the Atlantic. These sea breezes tend to meet in the middle of the state, forming thunderstorms. When I went to Florida State, it used to drive me crazy because I was up in this area, and I would see these big towering cumulus, big clouds right in this section of the state, and they would just stay there. Right? Some days they may move a little bit westward. Some days they may move a little bit to the east, depending on the overall flow. But I could see these in this part of the state almost every day from starting in late April. When I came back to school in September, they were still there. Interestingly, with thunderstorms, the most thunderstorms in the United States occur over Florida. You don't get them over Hawaii. Why is that? Because that air is trapped by what they call the trade wind inversion. So yeah, you get cumulus clouds building up, but they never get high enough to make thunderstorms. They can rain, but they don't become thunderstorms. Here is a definition of a severe thunderstorm. Has wind gusts stronger than 58 miles an hour, hail at least greater than 1 inch. Do you see anything in there that says anything about lightning? No. That's an interesting thing that's kind of missing in here. You could have a tremendous lightning storm and not have a severe thunderstorm. And flash floods also occur. So we've talked about vertical wind shear as being part of this. This is a classic synoptic pattern for the southern plains. And yes, this is part of your critical thinking. Look at this slide and answer that critical thinking question this way. You wind up with a low over Kansas, strong cold front coming through Texas, Oklahoma, warm front out north of it, a deepening extratropical low right here. What do you have coming in? Low-level jet. These happen a lot in the plains. All this is bringing maritime tropical air up. Oh yeah, you have a strong upper jet going through, helping to form this system with the divergence. So look at the wind shear. You have southerly winds one direction, northwest in another, maybe some continental tropical air coming in here to bring in even more heat. All of that can make some extremely classic severe weather events. Sometimes in the summertime, you get a stable layer. What happens is the air keeps heating and heating down below. You don't even get a cloud in the sky. But eventually, sometimes that layer breaks. You get a temperature up in this area, and all of a sudden it just goes boom. Big thunderstorms go up very, very fast. Now, if the layer never breaks, you never get the thunderstorms. Lightning. Lightning is weird. Uh, Everybody used to think it was generated by winds coming against each other, uh, literally causing friction, and from that causing a change of charge. Well, it turns out it's actually caused by graupel, which is kind of like a wet snowflake. What happens is graupel changes charge depending on its temperature. If the temperatures are less than 5 degrees Fahrenheit, graupel is negatively charged, and ice crystals are positively charged. So you have immediately a charge difference. And then, if you go temperatures greater, they flip. So, depending on what part of the cloud you're in, what kind of charge you're going to have with these things. Say you're in the higher part of clouds, you're going to be more like this. Lower part of the clouds are going to be more like this. So out of that, you get a change in charge and you wind up with lightning striking. Another problem with thunderstorms is downburst. If you're in an aircraft and you're flying on a glide path into or landing at an airport or flying out of that airport, you do not want to get into a downburst. The reason being the change in wind direction would be horrible for you. It is going to immediately impact how your aircraft performs. The stronger it is, the more intense it's going to change your glide path. So, say you're coming into winds coming at you, what happens is, well, you're going to have wonderful lift all of a sudden, so your plane's going to want to go up more. Oh yeah, all of a sudden you hit that, winds are coming straight down, and now you're really going downwards because your winds are coming with you. You've completely lost that wind, and if they're very strong winds, and sometimes they can be, they could be 75, 100 mile an hour winds. That's not going to do you any good. So, derechos are long-lived convective clusters. We had one in Ohio a few years ago. You had one in West Virginia. The same exact one. Actually, it went across Ohio. Actually formed over Chicago and went from Chicago on down across the Midwest through West Virginia, and eventually it hit my house in the late evening, almost around midnight, and I wound up with some trees down in my yard because of it. Here you can see a derecho forming out of just a couple thunderstorms, growing, developing into a big old bow as the winds are being pushed around it like a low up here. And here you can see reports of some of these derechos that have occurred. Hydrographs from flooding. Think about it. If you're in a downtown area, all the drainage is going through storm drains, right? Storm drains are generally designed to handle a 100-year flood event. Well, if I drop 3 and 4 inches of rain in an hour, that is going to exceed a 100-year flood event. So instead of winding up with, oh, I can handle this, it's not going to be able to handle this. I was in Arizona at a conference once in Tucson, and they happened to have a major thunderstorm that hit while we were there. Of course, it's a meteorology conference, so you would expect something like that, and wind up with a whole bunch of rain that hit very quickly. All the streets flooded, and the total rainfall was less than an inch. But they hadn't designed their system to handle that. Big Thompson Canyon is another classic example of where the mountains, and I just drove up Big Thompson Canyon this summer, and on the mountains there, you can get tremendous rainfalls up at Rocky Mountain National Park and all. The canyon itself is completely dry. But what happens is all that water runs off, rushes down a very narrow canyon. I mean, it is narrow. And goes through there, causes tremendous flooding. Hail's another hazard. It is water that's think about it, you have an upward drift in one part of the storm and a downward in another. They're right next to each other. So sometimes that raindrops get pulled back into that updraft and keep refreezing to get bigger and bigger hailstones. As bigger and stronger updraft is, the more the hail is going to be. And yes, dual pole, wonderful. I can detect these initial streaks, hail development in the cloud with dual pole. The only thing I can't know for sure is exact size of it, but I can watch it drop down in the cloud, and I can give you 20 minutes lead time, maybe, of hail going to hit your house. Tornadoes are the other thing. They are extremely intense, actually low pressure systems. They are driven by the fact that there's a very, very strong pressure gradient over a short distance. They have an exceptional air pressure gradient. Violent tornadoes, there's at least one instance of one tornado going over 1,000 miles on the ground. So you can see sometimes they can go really far. Other times they may only last a mile or less. And there are certain sectors of the United States that have it. Tornado Alley is a north-south corridor. We showed you earlier the classic for the Midwest, Great Plains. Secondary area is Dixie Alley. Guess what? We just looked at that one. And here you can see the different areas. But notice these are numbers per state. Notice how big Texas is, a pretty good sized state. So it's a bigger number. If you did it by area, Kansas, Oklahoma, Alabama, Mississippi become more and more pronounced. And there you can see that by squaring it to the area. Joplin tornado was one of the classic tornadoes that developed. It developed in 2011. The National Weather Service did a heck of a job in issuing a warning for this. They issued a warning before this thing even occurred out here. It was just developing. Now, if you lived in this part of Joplin, the time it took for them after they issued the warning to when that tornado reached that area was 1 hour. They issued an hour-long tornado warning. People were in restaurants in this area expecting the storm to hit when they first heard the warning, took cover, and about 50 minutes later decided they were not going to get hit. Walked outside, and there was the tornado coming through. It made a big question as to how long is the correct length for a tornado warning. Still up to discussion. And here you can see an EF scale, or enhanced Fujita. This was developed in conjunction with civil engineers, looking at damage, and from that estimating wind speed, which then we translate into this scale. And here you can see the classic tornado, a large hail tornado right in this part. I show you an EF5 this time, going through near Norman, Oklahoma. Moore, Oklahoma, you can actually see it descend and coming this way. And here is the classic signature. And you can see a very tight gradient right in this area where there's a tornado on the ground. I think that's about all I'm going to worry about with this. I hope you got something out of this. Let me know if you have any questions.